Alright, so this podcast has to do with emission spectra. And emission spectra kind of goes right along with atomic theory. And if you kind of remember back, we've already looked at Rutherford and Thomson and Dalton. Dalton was kind of the first one that kind of came up with a way to systematically explain atoms. And then Thomson, through the cathode ray tube, discovered electrons. And then Rutherford, with the gold flow experiment, decided there was a nucleus. Most of the atom was empty space. And kind of just the electrons filled that void that wasn't the nucleus. So when scientists began kind of burning certain elements, they found that if they looked through some kind of diffraction grating, that emission were given kind of like these. So you notice on lithium, instead of having just a full rainbow, if we shine just white light through a prism, or sunlight through a prism, we get a full rainbow. Well, lithium, it kind of gives a rainbow, but there's bright bands. Now, there's just bright red, there's an orange, there's kind of a aquamarine, and it's pretty faint to see, but here's a purple right here. Strontium, a bunch of reds, a bunch in the green area, and so on and so forth. Calcium, sodium is kind of just this bright yellow. The street lamps at night are sodium vapor lamps, and they kind of have that yellow glow to them. And as we kind of, again, start burning all these different elements, there's different, basically, fingerprints that each element has as it burns. Alright? So, scientists had to figure out a way to explain what they were seeing through these emission spectra. Alright? So, Bohr, and his first name was Niels, but Niels Bohr was kind of the guy that came up with an idea to explain what they were seeing, and really came up with an idea or a theory to explain what they knew to be true. Alright? So his model is known as the Planetary Model. And the Planetary Model is essentially something like this. Just like the solar system has our sun at the middle, and we have planets that rotate around the sun, or revolve around the sun. Basically, Bohr's model said the electrons kind of revolve around the nucleus, right? And they are only allowed certain orbits, okay? So depending on the atom, there might be different orbits that an atom, that the electrons exist for a given atom. Alright, so the explanation was something kind of like this. When we burn, or now add electricity to atoms, what happens is we excite those electrons. So they may start here on this first ring, and they get bumped up to a higher ring. Alright? And we say those electrons are in an excited state. Alright, so it's not where it should be, but it gets bumped up to an excited state. Likewise, electrons that start on the second energy level could get bumped up as well. Okay, so it's not just the first energy, the ground, or the electrons at the bottom one, but any electron can get bumped up to some sort of excited state. All right. And what happens is electrons don't stay in their excited state, but they drop down to their ground state. All right. So another term you need to know is the ground state, and the ground state is where they begin. Okay, or their typical starting point. So what happens is, this one right here might drop back to the ground state. It could also just drop, instead of the ground state, it might drop to another orbit. It's allowable. Or it could drop there. Again, this one might get jumped up that high, and it might drop down that much. Alright? But what happens is, it takes a certain amount of energy to get bumped from one ring to another ring. Alright? And that energy is what we say quantized. So it's a certain quantity of energy. Alright? So energy, again, is quantized. So I'm just going to put here, energy is quantized. And that simply means it comes in certain quantities. And again, this is all dependent on the type of atom we're talking about. And the atoms all have different orbits. So, certain energy is required to bump an electron up to an excited state, and that electron can fall to varying degrees. And essentially, a drop like this, alright, has a lot more energy than a drop like this. How come? Because it's dropping from, if it takes energy to get up, it's going to lose energy to get down, because energy is neither created nor destroyed. And then this little drop over here is going to be the least energetic of all. Okay? So when they drop back down, they lose energy, and that energy has to be accounted for in some way, because energy is neither created nor destroyed. So what happens is this small drop, all right, might be a little bit of energy, and that would be something like red light, okay, with a pretty big wavelength, and we get a red color. Maybe this middle drop would give us green light, okay, so a little bit smaller wavelength and green light. And maybe this biggest drop would give us blue light. Okay, so really small wavelengths, and it would give us blue light. So again, the way they explained this was, there's certain bands that our elements have. Alright, so strontium has these certain bands, because the energy levels, or the orbits that electrons can be promoted to their excited state, when they drop back down, there's only certain energies that are allowed. Alright, so we'll kind of explain this like this. If you have steps, alright, so here's some steps, maybe up to your house. Alright, so here's the ground, and it takes a certain amount of energy to walk up these steps. Right? Is it possible for you to step right here? Can you step there? And obviously the answer is no. We can't step there. That is not an allowable step. So just like there's certain steps, we can't stand between steps. Electrons can't fall between energy levels. So if we were to promote an electron up to this top level, it could not drop here, it couldn't drop to there, right? Because electrons don't exist there for a certain atom. So again, energy is quantized. There's only certain quantities that it can have for a certain atom. Just like steps or rungs of a ladder, you can't step between rungs of a ladder. You have to only step on the rungs. So those energy transitions correspond to various bands of light. It's always the same for every atom, because every atom has the same quantities of energy for its orbits. Alright? So again, Niels Bohr, the Planetary Model, and the evidence they had for this was emission spectra that had to say that electrons don't just exist anywhere, but there's certain energy levels that electrons can exist, and that gives us certain energy levels.